Yeah, hello everyone. Today we are going to talk about Vitess. I am Harshit Gangal. I work with PlanetScale, and I've been with this project for 9 years now. And today we are going to talk about the overview. We'll take you through the architecture of Vitess, then talk about some new and upcoming features, and then my colleague will present query serving demo, and then we'll open up the floor for Q&A. So what is Vitess? Whenever you think of sharding, you should think of Vitess. That's how we relate. And it's cloud native. You can deploy on Kubernetes. We have an operator that can easily help you deploy on Kubernetes. And it was built in 2010 in YouTube. And from there, it was always been stateless. It's really easy how it does failovers and it detects failure detections and how it recovers from itself. So it's built from the ground up and being cloud native from day one. It is massively scalable. You can basically, there's no theoretical limit to how much you can scale your database with Vitess. And it has been highly available with the VT org we have, which does the failure recovery and detection. And this is wire compatible with MySQL with all the different versions. Why you want to use Vitess? I already talked about sharding, but when you use a single node MySQL, what happens? You get a write contention. If you're using cloud provider, then you hit IOPS limits. You see deadlocks. So there's no way of getting around it. Then also you see like backups taking a lot of time. So if you have like failures, your nodes going down, then it's take a lot of time to even do the disaster recovery over there. There's a limit to a single node that you can scale your primaries. So then you say, okay, let's move our reads, and then you scale out your reads by adding more and more replicas. And that leads to more and more replication lag, so that creates another problem for you. And then there's a physical limit to where you can exceed your instance size. So at that point, you have to see, okay, now we have to do sharding, and there's no way going around. So by doing sharding, you basically get rid of all of these problems. You get a faster backup restore time, so your disaster recovery is much, much faster because you just keep sharding. You have small instances, and you can basically then have a faster recovery over there, and then your write condition also goes away because each primary that have in different shards will basically have less and less QPS to handle. And because it has less and less QPS, the replicas also being faster, and it will keep up to date with the primary. And then you just keep on scaling, and you keep resharding going further. It works with all the known ORMs and frameworks. You can use any database viewer UI as well, and all which works with MySQL just works with Vitess. And we have a very active community. We have 15 active maintainers. This is some of the numbers I pulled for a year from devstats.cncf.io. You can also go and check it out. Like in a year, we got like some 1,700 PRs opened. We did like 101 different PR authors, 36 companies contributed to it, and there were like 27 new contributors. Let's see some of the companies that are using Vitess in production. Flipkart was one of the early adopters when I was there at Flipkart back in 2016-17. And then GitHub is running in production the PRs and the issues database that you see and use every day in your life. Then there's Slack, who's running like 100% of their database by using Vitess. And and there's PlanetScale, a cloud company which provides a database as a solution. That's all powered by Vitess. So these are some of the terms I'll use, and also my colleague will use when he goes through the demo, and I'll go through the architecture. So Keyspace is a logical database. It's something similar that we have in MySQL, but here it's like a collection of physical databases underneath. And we have shards, which are the subset of Keyspace, and each shard contains one primary and multiple replicas. At Vitess, you have to define something called vSchema, which is a configuration to give to Vitess to understand how your sharding is working and which table resides in which key space, and what to use when you when you send a query, then it understands how to basically send your data to which shard. And Windex is the internal to vSchema, which is the sharding function the Vitess will use to know where your data resides and where the data has to be sent to retrieve the data. So this is the architecture of Vitess. The entry point for your application will be the VT gate, and that talks MySQL protocol. Also gRPC is there, but you can talk MySQL protocol. So all the open source MySQL drivers that are there can just connect to VT gates. So once you are connected to the VT gate, you can also use in between a load balancer, so that it can do VT gate discovery, and then you can route to one of the VT gates. Once you are connected to a VT gate, then you send a query, and the VT gate will do the parsing of your query. It will understand your query and then use the vSchema to plan your queries. And once your query is planned, then it will send to the appropriate shard. In a shard, we have some sidecar VT tablet running along with MySQL, where your data will reside. So when your data goes to VT tablet will basically do the persistent connection pooling for you at the sidecar level, and it will then send the query to MySQL, and it will retrieve the data back and send it to VT gate. So VT gate also will do the aggregation if needed based on what kind of plan happened and what kind of query you have executed. So that's the query serving path, and then we have the control plane. So in the control plane, we have a VT admin, which is the UI part of the control plane where you can visualize everything. And then you have the VTCTL, the CLI, that will be used to basically make modifications to your cluster. And that information will be stored in the topo. The topo server is the metadata store we have. You can use HCD or Zookeeper. And we have some VTORC, which is the failure detection and recovery module of the Vitess, which keeps monitoring using the topo server that what are the different shards and what are the primaries, replicas, and it will fix any issues that it detects. So some of the features. There are a lot many, but I've just listed some of them. So MySQL compatibility is the first thing, and it's a moving target. As MySQL keep evolving, we also evolve with it. So we keep adding. So most of the things that MySQL supports should be just supported in Vitess. We keep adding more and more as we go forward. Resharding, so I talked about that you have to shard, but then you also need a way when you hit those limits, then you have to again reshard. So it's very seamless to how we do resharding in Vitess. There's something called materialization. So it's basically you can use that to do change data capture. You can use to do materialized views, which you can keep real-time updated, not the MySQL views, but the views that will be updated on the fly, and you'll have the near real-time views available to you. We have seamless online schema changes, so you can do migrations with no downtime. And we have the backup and recovery, where if you bring up any new replicas, it will basically it will take it from the backup, and then it will plug it into your cluster, and it will also start the replication from the last point it knows where the backup was taken from. The query consolidation is an interesting feature. What it does is whenever you have a high spike, whenever the spike in your traffic, and you see some rows are getting hit very frequently, what it does is, if I showed you that there's a VT tablet, what it does intelligently is it keeps checking what are the queries that are executing, and if it sees the similar query being executed many times, only one of the queries gets sent down to the MySQL to retrieve the result. And it does the buffering at VT tablet level, and once you get the results, that goes back to VT gate to send it to the client. So it avoids sending all the herd down to MySQL and avoiding any downtime or ooms happening at the MySQL level. And I already talked about we have VTORC, which does the failure detection and recovery, so you won't even see. It basically try to help you keep high availability around. Some of the new features I want to highlight. So this is recently added, atomic distributed transactions. So earlier we used to support distributed transactions, but that was the best effort. And now we want to make it atomic, which means everything gets committed or none get committed. So now the application does not have to worry about whether is there a partial commit happened or not. So we are able to take care of making it atomic across the shards. Recursive CTs is also being one of the asks that has been there from the community, and we have added the feature. There is something called VT Toolkit, which is a new thing we are working on and adding more to it. It will help you drive your adoption to Vitess. Basically here you can give your query logs and you will understand what kind of different tables are grouped together and what are the query columns that you're using to join those keys. And that will help you define your V schema. And then you'll keep iterating to have a better V schema, because V schema will define you how your queries will be routed. And you want less and less work to be done at VTGate because it's an aggregation layer, and you want more to go down to the MySQL, which eventually means that you have less round trips happening at VTGate level. So this toolkit is what we are seeing as people getting better in designing their V schemas, and they can have a better query latency at Vitess. We also added foreign keys support. So InnoDB is very tricky in doing these foreign keys. So we build all that logic at the VTGate level so we can do seamless online migrations and everything, because otherwise a lot of things were hidden, that how foreign keys were handled by InnoDB, but we brought all that logic to VTGate so that everything is visible now, and our internal tools which use the V replication flows like online schema and resharding and stuff can continue to work well. We have something called multi-metric throttlers. So I talked about like we do resharding, we do online schema change and stuff, which can bring down your primaries if you're not throttling properly. So all these internal tools which keeps running for a longer duration, like because your schema changes can happen like for days or weeks based on how much data you have. So we need a mechanism that doesn't bring down your replicas. So we have a throttler in place which slows down if we see your application traffic is increasing. So we just slow it down. So that's basically handle it. And why it is multi-metric? Because you can also plug in your metrics that you want this throttle to watch for, so that it can slow down accordingly. And we recently in the operator we added like autoscaler, which also helps you auto-scale VT gates as your traffic is increasing. And now with that, I'll just pass on to my colleague who will take you through their demo.
Hello, folks. I have the mic. I am Manan. I'm also a maintainer of Vitess. I work at PlanetScale as well with Harshit. So today I'm going to be taking you through a Vitess demo. It's going to be a demo that's going to showcase the capabilities of Vitess with regards to query serving, how queries are routed through the VT gate, how do we collect the data from VT tablet, and we're also going to look at how sharding works. So this is the VT admin page. I already have a cluster set up initially for us. For the purposes of this demo, we are only going to look at the commerce key space. The unsharded key space, we can talk about it in the end if we've got some time left. It's basically used for sequence tables, which is like a way to get auto-increment to work in a distributed system. So we can talk about sequence tables in the end if we've got time left. But for the initial demo, we're going to look at the commerce key space. My colleague already talked about how a sharded key space is going to have multiple different shards. In this case, I've sharded the commerce key space into two different shards, -80 and 80-. The nomenclature of these shards is going to get a little bit clearer in a little bit of a minute. For now, in the commerce key space, I've got two tables. I've got a customer table and I've got a C order table. So if you look at the customer table, there we go. The schema for the customer table is very straightforward. We've got a customer ID and we've got an email. Those are the only two fields that we're storing. The primary key is the customer ID, and right down below is where you see the Windex information. So what happens is, because you've got a sharded table, when you try to insert a data, for example, let's take an example. Let's say I'm trying to insert a row into the customer table where customer ID value is 1. Now Vitess needs to figure out which of the two shards. We saw there are two shards, -80, 80-. Vitess needs to figure out which of the two shards is it supposed to insert the data in. So for that, we have a Windex, which is what we specify in the V schema. What this Windex is saying is that we're going to use the customer ID column. We're going to run it through the reverse bits Windex, and the value that it gives us in the end is what we will use to know which of the two shards it's supposed to go in. So what happens in this case specifically? So when you do customer ID insertion of row 1, your input is going to be value 1. What reverse bits does is it just reverses all the bits that you gave in as the input. So customer ID value is being 1. Reversed, it becomes 1 followed by multiple zeros, which is the value of 80. So that is what the meaning of the shard is. So hyphen 80 means all the values for the value that the Windex provided from 0 up to 80 is in the first shard. Everything which is equal to 80 and higher than that is in the second shard. So that's the name of the shard, 80 hyphen. So everything 80 onwards is in the second shard. So if you take the value of 1, after running it through the reverse bits Windex, we end up at a value of 80, which is greater than or equal to 80, so it ends up in the second shard. Similarly, I've got a few more examples all going through the same process, 1, 2, 3, 4, and 5. If you look at the value of 2, reversed it, we get 0, 1 followed by 6 zeros, which is 4, 0. And because 4, 0 is smaller than 80, it ends up in the first shard. Similarly, and so on. So this is how sharding works. Vitess has a bunch of inbuilt Windexes, reverse bits, XD, XX hash, a bunch of others. But it's also pluggable. So you can choose to have your own sharding scheme as how your data is according to your application. For this specific example, for this demo, I've chosen reverse bits because it's got a very neat property where all the even values end up in the second shard, and in the first shard, and all the odd values end up in the second shard. And the reason is that 80 hyphen and 81 000, 1 followed by all zeros, the value is greater than that only if your first bit is set. And that is governed by the last bit because we're reversing through them. So it becomes like an even odd property. So it's very good for a demo because you can really show the distribution of keys. So I've got the cluster set up over here. I'm going to connect to the VT gate. We're going to insert some rows into this. And if you go ahead and look at the data, so this specific syntax that I used over here, use commerce 80 hyphen, is a specific syntax applicable only for Vitess, where we are basically asking the VT gate that for the next queries that I'm going to execute, specifically go to the 80 hyphen shard and only get me data from there. Do not go through the entire key space, specifically get me data for the 80 hyphen shard. So when we do select star for customer, we actually end up seeing that the first 3 values, 1, 3, and 5, the odd values end up in the second shard. And if you look at the first shard, we've got the even values there, 2 and 4. So this is how sharding works in Vitess. We can go ahead and now look at the order table. So this is the second table that we have in our schema. We've got order ID, we've got a customer ID, and we're storing the product as a string for now. I didn't want to complicate the demo a lot, so I didn't introduce a third table for product as well. But the getting started guide that we have on the website for Vitess actually has the 3 tables. It's called the order, product, and the customer table there. For the purpose of the demo, I'm just storing the product as a string right now. And we see it's again using the same reverse bits Windex, and the column and the sharding key over here is also customer ID. This is going to be important when we look at the query serving for Vitess. We're not sharding by the order ID, but by the customer ID. And we're going to see right now why that is useful. So I'm going to go ahead, insert some more rows into this. I'm going to have 6 orders, and a few of them for different customers. For the first customer, there are going to be 3 orders, and 1, 1, 1 each for 3, 4, and 5. If we go ahead and we now look at the data, we already saw that for the second shard, 1, 3, and 5 customers were residing there. The extra property that now we get, because we've chosen to shard by customer ID and not by order ID, all the orders for a given customer, for customer 1, we see that all of their orders are in the same shard where their customer row was also living. Same goes for 3 and 5. And here we see that the order for customer 4 is here in the second shard. Had we chosen to shard by the order ID, we would not have had this property. Instead, we would have seen a more even distribution of data. Right now, you see that the customer in the order table, we've got 5 rows going to the first shard and only 1 row in the second one. But had we chosen to shard by order ID, we would have seen a more even distribution of 3 and 3, but we would have lost this property where the data for a given customer would have been co-located in a single shard, which is the case right now. We can go ahead and now look at how Vitess serves some of these queries. So MySQL offers a command which is like an explain command, which shows how the internals of MySQL work and how the plans are created, how MySQL is going to execute them. VExplain is like it's a similar command, but it's Vitess explain. So that's why you call it VExplain. And this shows how Vitess is going to route the query for you, how VTGate is going to run this query. So if you take a look at a very straightforward query, select star from customer. If you want to collect data from the entire key space, all VTGate needs to do is gather the information from both the 2 shards, combine them together, and send them back to the client. So here we see that it's a scatter route. What this basically means is that Vitess is going to go to the commerce key space, and it's going to send this query, select customer ID, email from customer to both the shards, collect the data, and send them back. If we were to execute a query which had a predicate on the customer ID, in this case, Vitess is smart enough to figure out that because your table is sharded by the customer ID, it knows that this row can only live in the second shard because the customer ID value is 1, and that cannot be in the first shard. So what Vitess does in this case, it uses an equal unique type of a routing. It uses the reverse bits index, uses the value 1, figures out which shard it can route the query to, and only sends that query to that one shard. So this is how you, this is why sharding by the correct key becomes important for your query latencies, because you want to reduce as many of cross-shard queries as you have. We can go ahead and look at the same for the order table as well. Similarly, if we were to query the order table for a given customer, want to get all the rows back for a given customer ID, we see that it is also an equal unique thing. Slightly different from the previous example is that customer ID for the customer table was also a primary key. So we knew we were going to get back only one row. In this case, it's not really the primary key, so we're going to get back multiple rows, but because we chose to shard by customer ID, Vitess still has the property that all of those rows, even if there are multiple rows, will still live only on a single shard, because we've chosen to shard by that customer ID. So this gives us that property. One additional thing that we're going to look at now is if we ask Vitess to gather the orders for a given specific order ID. In this case, order ID is the primary key, so we are aware that we'll only get back one row, but because we've not chosen to shard by that, Vitess doesn't really know which of the two shards this row lives in. So even though we know that we're going to get back one row, Vitess has to query both of those shards to even figure out whether the data lives in that or not. So this ends up becoming a scatter query, even though we know that we're only going to get back a single row back. We're going to get back to this query. We're going to look at a way of optimizing this as well using a secondary index. But before that, I'm going to quickly cover how joins work. A slightly more advanced plan. If you look at the query that we tried to execute, it was a very straightforward cross join that we did between the two tables, the order table and the customer table. In this case, what Vitess needs to do is it needs to gather all the information for the order table, gather all the information on the customer table, but because the information resides on two different shards, it has to do the join on the VT gate level, on the proxy level that we saw in the architecture diagram, because it has to pull in the data from the two shards separately. So that's what it does. It does a scatter query to gather all the information for the customer table and gather all the information for the order table, and then it does a cross join on the VT gate level. These kind of operations are generally expensive because you're doing the join on the VT gate level, you're storing, it's in memory. So all the rows that you're going to get back, all the 25 rows that you're going to get back is going to be stored in memory for the duration of this query. In contrast, if we look at a different query like this, where you are joining, but you're also giving a specific predicate where the customer ID values are equivalent. Because we've chosen to shard both the tables by the same column and you're using the same index, we know that all the qualifying rows will come from each of the two shards, but the join can be pushed down to MySQL, because all the rows for a given customer for those orders were also on the same shard. So in this case, it is a scatter query, but it is no longer a join that VT-Gate needs to process on the VT-Gate level. We can push that work down to MySQL. So this is the query that we end up issuing to both the two shards, which is a join in itself. So we talked about how when we were querying the order table, we had to do a scatter query when order ID was 1. So one additional feature that Vitess has is for secondary indexes. We already saw that the primary index was used to define how sharding works for a specific key space, specific table. We can introduce secondary indexes as well. I'm real quick going to create a secondary index, and it runs a workflow which can be seen over here. So if in case you've got like a huge table and you see that, okay, you're going to do one more additional query point and you want to add an additional index. So in MySQL, you can add an additional index on each of those tables. On Vitess, this is the equivalent of an index that you would add. It's called a v-index, and what this does is that it stores the mapping for that column against the key space ID. I'm going to externalize it, and then I'm going to show you what I mean by that. So if you see, we originally had only two tables, customer and C order, but after we created a index, the secondary index, we have an additional table. And if we look at the data that's stored in that table, it has a mapping from each of those order IDs to the key space ID. And this tells us which of that shard the order ID is living in. So if you look at order ID 1, this has the key space ID that we saw using the reverse index, that it maps to 80, and that lives in the second shard. So it stores all of those information for each order ID. So now when we query Vitess and we ask it to explicitly route a query for a given order ID, Vitess can do, what Vitess now does is that it first asks the secondary index that we created, for this order ID, what is the key space ID? Once it has that key space ID, it can use that to route the query to that single shard. For the specific example that we have over here, it doesn't look like a lot of improvement because we're still doing two queries. We're doing a Windex query, and then we're doing a normal query. And the original example, we were just going to do two queries to the scatter. But this immediately becomes beneficial when your number of shards increase. So this is a very scalable approach because even if you have 256 shards, this approach will still only do two queries because the first query would be to a Windex, which is going to be a single query, and it's going to ask for the key space ID. And using that, we're again going to do a point query to the specific shard. So this is how secondary indexes help out in query performance improvements. That's all for the demo. I hope that was beneficial for you. And we're going to open it up for questions now. Thank you so much. So secondary index is also stored in the same key space where your table is, because that secondary index is going to be as large as your original table, right? Because for each of the rows that are there in your original table, you're going to have one mapping in the secondary index. So that also gets sharded. So if you, I didn't go into the details of it, but if you look at the command that I wrote over here, we're actually telling it which index to use for the secondary index. Because the secondary index itself is a massive table, it also needs to be sharded. So we're going to tell it how to shard that table too. So it's stored in the same key space and as a sharded table itself. Yes. You want to take this?
Yeah, it's fine. What you exactly want to know about the atomic distributed transaction? Like, earlier what we used to do was we use best effort. I think echo. From the design point of view, what we do is at the commit time, we basically check like how many shards your your transaction has went to, and from there we store the metadata. Like we store all the queries that you have executed in that transaction, and that is what we use to do recovery if your commit flow fails in any point in time. And what we do is whenever there's a commit flow fail, it could be because your VD tablets went down, MySQL went down. And that time, whenever they come back up, first we do the prepare of all the open to atomic commit transactions, and then we allow any other query to come through. So it basically whatever the locks that the original transaction was holding will hold the lock first before proceeding forwards. And then we have a recovery way of making sure that if the commit decision was made, then it ensures that the commit happens atomically on it.
I'll just add a little bit to it. So the two-phase commit basically works by guaranteeing that once you've decided to prepare a transaction and a shard has said that, okay, I will prepare the transaction, it can no longer refuse to commit that transaction. That's the guarantee that you're expecting from a two-phase commit protocol. That's how it works. So because we're using MySQL as an underlying storage, MySQL doesn't give us that guarantee that even if we've issued some queries, it doesn't give us the guarantee that when we try to commit it, it's going to roll forward or not. So we had to implement all of those features on the Vitess level, where we keep track of what all DMLs have been issued so far in that transaction. We hold the logs for those. So even if MySQL crashes and it fails with this and we're not able to commit the data, when MySQL recovers and we start a fresh and new MySQL instance, we do the recovery first. We open all those transactions that were prepared previously so that all the transactions in a distributed sense end up being atomic. Anything committed on one shard also ends up with the same guarantees on the other one.
It's similar to how exe works, but exe is too chatty and made it like unusable. And the thing is, exe, you have to decide whether you are going to do like cross-shard transactions or not. But with this, it's more flexible, and we decided at the commit time and not at when the transaction gets opened. So that way, it can take the benefit when you're only doing single shard transactions. Then it knows that okay, you don't need the atomicity guarantees because that is delivered by MySQL itself. So only when at the commit time we basically do a lot of stuff, which how the 2PC works, but it's only the decision that is made late in the commit rather than at the starting of the transaction. So that basically gives you more benefit in the time, like the commit time basically reduces rather than having if we start using exe. And exe is also like some of the things that we don't want to use because it's not, we are not fully, we don't have that exe is more robust at that point. So we want to use existing MySQL level guarantees that are already there and build on top of it.
So you can, in that case, you would create a unique index, which makes sure that, yeah. So we have indexes of different types. There's a consistent lookup index, there's a lookup unique indexes, which basically if you try to insert duplicate keys, then it complains. I'm sorry.
From VTGate, you can basically do the vStream API, and that will be collecting from all the shards. So you will have a single endpoint to get CDC. Yeah.
Consistency guarantees across cross-shard queries. It's the same guarantees that MySQL provides. Everything, yeah. I'm sorry, I don't quite get it.
So for the cross-shard, you'll basically see read committed isolation if that's what you're looking at. Otherwise, what is get persisted by the MySQL, you'll just see the same guarantees that follows. Yeah.
That's one of the advantages we get because we're using MySQL as our storage layer. The guarantees that MySQL has kind of flow through into Vitess as well.
Why not use MySQL as your backend on your Topo server instead of HCD or
So Topo servers, specifically we use etcd because they have features like they run backstores and raft there, and we use them for locking the shards so that VTR, multiple instances of VTR don't clash with each other when they're trying to recover the topology, because that would be very problematic if two different VTR instances decided to promote two different primaries. So to avoid all of that, we use etcd because it's running a consensus protocol there.
We have similar tool for Microsoft.
We are not aware of it. This supports, we know something for Postgres, but I am not sure about MySQL server. Right. So stored procedures we don't support because it just gets too complicated. We support for unsharded, but views is supported. You can do views sharded. We have a good enough support, and yeah, your views should just work cross shard. It's there. So that you have to configure at the MySQL level. We as a layer on Vitess, like I don't think we have that support from the Vitess level, but you can configure directly at the MySQL level, and that should work. Yeah.
How do you ensure high availability? You have two shards, one shard goes down.
Yes, so the high availability is guaranteed by the VTORC instance that we had in the architecture slide. So VTORC is a fork of orchestrator. I'm not aware if the orchestrator is a MySQL, it was a high availability tool that was used for MySQL clusters, and we forked that into Vitess. And what VTOR does is that when you run a single shard, you've got a primary instance and multiple replicas. When a primary crashes, VTOR, because it's pooling all of those instances, MySQL replication also breaks. It immediately figures out that, okay, the system has crashed, and then it promotes a different replica into that. So it's configurable. By default, in the examples that we have, we generally keep 3 replicas. So you've got a primary, you've got one replica, and one read-only tablet for backups and stuff. But it's configurable. You can choose to have as many replicas as you want. It's something that it's dependent on your application. If your application has a lot of read traffic and you want to have like 5 replicas, that is totally possible. You can also choose to configure how many semi-sync acts you want to run with. So we're using the same MySQL replication thing for our clusters.
So every replica comes up with its own storage?
Yes.
So every replica, so you're replicating data, right?
Exactly. So it's each shard.
You don't need a shared storage, right? Every replica comes up.
Exactly. So it's each shard is in itself a MySQL cluster where there's a primary and multiple replicas. They have their VT tablets attached to them, but in a sense, it's still a MySQL replicated environment. So there are multiple MySQL instances running per shard.
I'm just drawing parallel with Postgres. So like when you do partitioning a lot, right, the planning takes a lot of time.
Yes.
So how much latency does that mean?
So
So how we work, sorry, ahead.
Yeah, yeah, go
Yeah.
ahead.
So how we work is basically when we send a query, we parse the query and we normalize the query, and then we do the planning. So when next time when you send the query, we have the plan cache ready, so we don't take time the next time. So it's only the first time you'll see the latency, but forward you won't even know what the planning time is.
Yeah, so I'm just going to real quick show this over here. Over here, if you see that order ID 1, we don't actually have the 1 value in the plan. The plan just shows a normalized value for order ID with this. So even if you ran the same query where you said order ID equal to 5, it would still use the same plan because we just build it once and then we cache those plans.
I have a question, like how the order by query works this chart.
Right. So.
Let's consider it for the million, like million records. Now,
So how the planning works is, like, if we can send the order by down, if you use the sharding key, then we can easily do is what we do is we send the order by down to all the MySQL. So local ordering happens at MySQL and we do the merge sort at VTGate. But if you're using some other column which is not part of your Windex or anything, then we have to do all the ordering at the VTGate level. That's how it works.
All right, thank you so much for joining us today. See you all later.
Yeah, thank you.